Okay, let's unpack this. We are diving deep into one of the most frustrating and persistent dilemmas in modern AI.
Mm,
We have these incredible deep reinforcement learning algorithms, DRL, that can, master complex video games, robotic maneuvers,
absolutely. Superhuman performance in some cases.
and yet they completely fold when you give them a seemingly simple, real-world, multi-step task.
It's the AI version of being a grandmaster at chess, but completely unable to follow a recipe. We're talking about tasks like making a meal or assembling flat pack furniture.
Or in the world of AI research, these really complex crafting tasks.
Exactly.
And the root cause is this fundamental weakness in DRL. It's like, imagine you have a giant digital haystack, and the only reward you get is for finding one single very distant needle.
Right. And if you have to take 100 specific steps in the perfect order just to get that one win signal.
The agent just wastes millions, maybe billions of trials blindly wandering. And this is what researchers call the sparse-reward problem.
And that's because DRL is an inductive learner. It learns from just massive trial and error processing raw data like pixels or sensor readings. It's incredibly powerful, but it's just deeply inefficient when that successful path is long and rare. It has no structure.
Which is where its theoretical opposite, classical planning or CP, comes in.
Mhm.
CP is a deductive learner. It's brilliant at finding the perfect sequence for these big hierarchical tasks, but, and this is the big but,
But only if you first give it a perfect, detailed rulebook, a symbolic manual that spells out every action's preconditions and effects.
so you've got this tension. DRL is the master of low-level action, but gets totally lost in the big picture.
And CP is the master of the big picture, but it needs a human to write the manual for it first.
The mission of this deep dive, then, is a framework designed to bridge that exact gap. The system we're looking at integrates the powerful, adaptive execution of DRL with the structured logic of classical planning.
And the key is, it does it without demanding that manual.
It automatically generates the rulebook from just a few observations. It literally writes its own instructions.
So to build that bridge, you have to solve this core problem of representation. DRL sees the world as a bunch of continuous numerical vectors.
Low-level state space.
Yeah,
Things like positions, velocities, pixel values.
right. But planning needs high-level, discrete logic. A planning state space where things are either true or false, inventory has wood, or agent is at the workbench.
And you have to connect those two worlds. You've got to tell the agent, look, all that running around you're doing, it's just noise until you hit one of these symbolic checkpoints.
Exactly. And that checkpoint is the concept of a critical action. These are the crucial high-level symbolic actions that are absolutely necessary for making progress toward the goal at that planning level.
They're the moments that matter.
They're the moments where the environment changes in a really meaningful, symbolic way, no matter what little low-level movements led up to it.
Can you walk us through an example? The source material uses a really good one from a resource gathering task, sort of like Minecraft, right? Crafting a stick.
Yeah, that's a perfect one. So let's start with the low-level reality. The agent's in an 8x8 grid. Its raw actions in that system, the Markov decision process, are just up, down, left, right.
And those actions on their own don't change anything symbolic, like your inventory.
Not at all. But the critical action, the moment that truly matters, is make stick.
Okay.
So make stick is the symbolic critical action. The low-level action that might trigger it could be called make one. And for the system to know that this critical action actually happened, two preconditions must be met.
The rest of
The
it.
recipe. The agent has to be standing at the workbench, and its inventory has to have, let's say, at least 2 units of wood.
So it's tracking location and inventory numbers. If the agent gets to the workbench and hits make one,
The effect is that the inventory state changes. Wood goes down by 2 and sticks go up by 1.
and that is the fundamental mapping we were talking about.
That's it. A long, messy sequence of low-level moves, walk right, walk up, turn around, is only considered a symbolic transition in that high-level plan if it ends with the successful execution of one of these critical actions.
It's the moment the messy numerical world of DRL produces a clean, logical fact for the planner to use.
Exactly.
It's fascinating. So the whole framework depends on having this precise map of critical actions, preconditions, effects. But the innovation here is that this map isn't given by a person. The agent learns it.
Right. And this brings us to the two-stage framework. Stage 1 is induction, and stage 2 is training.
So stage one is the reverse engineering phase.
Yep. The goal of this induction module is to induce the full symbolic knowledge, what they call the critical action schemata, from just a few short expert demonstrations. It's like the agent watches a quick YouTube tutorial and has to figure out the game's physics from that.
And it does this in three very specific steps. The first is just filtering the noise, right? Extracting action effect linkages. How does it figure out which of the thousands of possible actions actually matter?
It calculates something called mutual information.
Yeah.
It's a measure of dependency between two variables. So if a certain action always, and I mean always, happens just before a specific variable changes.
They have high mutual information. They're probably linked.
You got it. So an action like move right has almost no mutual information with the stick count. But the make one action, it has an extremely high mutual information with the variables stick would. It's a really powerful filter that just cuts out 99% of the irrelevant stuff immediately.
Okay, so that's step one. Now we know which action is linked to which variables. Step two is determining the effect symbolic rules. We know make one affects would, but how? Is it one would? Two?
We need the formula.
And this is where the methodology gets really interesting. Instead of just standard regression, they use genetic programming, or GP.
Why? Because GP is designed specifically to find the structure of an equation, not just the numbers. It's an evolutionary approach. It starts with a whole population of random little programs' formulas, basically represented as expression trees.
So it's literally just throwing equations at the demonstration data to see what sticks.
Yes, iteratively. It tests these equations against the observed changes. The programs that most accurately predict the outcome, the ones with the highest fitness, they get selected, mutated, and combined to create a new generation of programs.
And over many generations, it converges on the actual mathematical rule.
Precisely. It's an incredibly powerful way for the system to evolve its own laws of physics for that world. It can conclude when action make 1 happens, the would count at time t plus 1 equals the would count at time t minus 2.
It discovers that numerical rule.
It finds that rule, would plus 1 equals would t2, with very high accuracy. And then finally, the third step is determining precondition rules, which is a bit simpler. It's a classification problem.
Classification means, is it true or false? Do you have enough would or not?
Exactly. They use decision trees for this. The system just looks at all the states right before a successful critical action and asks what had to be true for this to work. And that determines the binary preconditions, like you need 3 stone and 2 sticks to make a pickaxe.
So stage 1 complete. The messy demonstration data is now a clean, structured, rule-based manual of critical actions. Now we get to stage 2, training. How does this beautiful new symbolic knowledge actually guide the DRL agent?
The structure becomes the agent's internal compass. Once the rules are induced, the training module takes a final goal, let's say acquire iron, and it uses that new rulebook to build a step-by-step roadmap.
And it does this using a logic technique called backward chaining.
Clanning in reverse.
To get iron, I need a stone pickaxe. To get the pickaxe, I need sticks and stone. It just chains all the way back to the start.
And that entire dependency chain is formalized as the critical action network, or CAN. It's an in-tree structure showing all the subtask dependencies. And this network, this CAN, is the secret weapon for solving that sparse-reward problem.
Because it lets you implement intrinsic rewards.
You got it.
So instead of only getting that one massive distant reward at the very end,
the agent gets helpful little nudges along the way, guided by the structure it just learned.
How does that work in practice?
The DRL agent, which uses PPO as its backbone, it gets a small, positive, intrinsic reward, like a +1 score, every single time it successfully completes a critical action that moves it along the path in that CAN.
So it converts that single distant goal into a dense, helpful sequence of immediate sub-goals.
Exactly. Craft a stick, you get a reward. Craft a pickaxe, another reward.
The agent is constantly being reinforced for making structural progress, even if the final goal is still miles away. This feels like it should solve the exploration problem, but how did it actually perform against the current state of the art?
The validation was pretty extensive. They tested it across 3 different simulated 8x8 grid worlds. First was door key, which is a standard hierarchical task. Find key, open door, toggle switch.
Okay, a common benchmark.
Then they used a switch environment, which was designed specifically to punish random exploration. The 8 switches task, for instance. The agent has to toggle 8 switches in a very precise sequence. And crucially, if you toggle the wrong switch, you go backwards. Your progress regresses.
Oh, so random exploration is a disaster. You just constantly be resetting yourself to 0.
It's practically impossible, yeah. And finally, they use the complex Minecraft environments, like a task called enhanceable, which requires a really deep sequence of multi-step crafting.
So what were the results?
They showed what you could call a performance cliff. The proposed framework was tested against, every relevant baseline, DRL algorithms like DQN and PPO, imitation learning like behavioral cloning and jail, exploration techniques like RIDE.
And on those really tough tasks.
The gap was catastrophic for the baselines. On the most difficult long-term tasks, so 8 switches and that enhanceable task, all the other methods, they just completely failed.
What do you mean failed?
I mean, they achieved essentially 0 success within the 5 million step limit. They just never found the path.
And the integrated framework?
Achieved near-perfect scores. And it did it fast. It confirms that for these long, sparse reward problems, having that structural guidance isn't just a nice-to-have, it's a hard requirement.
Right. If you're just relying on pure reward-based exploration...
You simply will not solve these problems.
I think it's important to dig into why the baselines failed, though. Why would an imitation learner like jail, which literally copies an expert, fail on enhanceable?
That's a great question. So imitation learning is good at copying the specific trajectories it sees. But enhanceable requires the agent to compose new sequences, to generalize beyond the exact demonstration.
So the demo might show you how to make a stick and how to mine stone.
But it doesn't show you the exact 20-step sequence to combine them into a final complex tool. Without the underlying symbolic rules, imitation learning can't adapt or generalize that structure. It can only parrot what it's seen.
And what about efficiency? On a simpler task like Dorky, where other algorithms could eventually solve it, did the planning structure still help?
Oh, absolutely. The framework was highly sample efficient. On Dorky, it reached a high success rate much, much faster. It needed significantly fewer training steps than even a strong baseline like PPO.
Because it wastes less time wandering around.
Exactly. By defining the milestones up front, the agent is focused on hitting the right critical action at the right time.
So the system performs better, but I think the really compelling part here is the generalization capability. They said it happens at 2 different levels.
Yes. The first level is task-level generalizability. This is where the agent learns the rules for, say, a 4-switch task and can immediately apply them to an 8-switch task.
It knows the switch rule, so it can assemble a longer, novel sequence it's never seen.
Right. It's composing known verbs into a new sentence. But the second level, rule-level generalizability, is where the power of using genetic programming really stands out.
This is where it's more than just a clever planner.
This is truly disruptive. They tested a scenario where they actually changed the fundamental rules of the world. For instance, changing the crafting cost of an item, or switching the activation order of the switches from n+1 to something like 2n+1.
So the agent's laws of physics were suddenly wrong.
They were. But because genetic programming was used to induce those rules in the first place, the system didn't need to retrain from scratch. It just needed a few-shot demonstration, a tiny handful of new examples, to reinduce the revised rules.
So the GP can evolve and adapt to the new reality.
Exactly. The induced programs are adaptable. They can quickly evolve to model new substructures, which is something a traditional DRL system would find almost impossible to handle without massive, massive retraining.
Let's bring this all back to the big picture then. What we're really seeing is a sophisticated combination of 2 fundamentally opposed traditions in AI.
That's the perfect way to put it. It successfully uses the massive low-level power of inductive deep reinforcement learning for dealing with complex, high-dimensional worlds.
And it marries that power with the efficiency and robust planning of deductive classical planning.
And the genius move is that automated inference. Using tools like mutual information, genetic programming, and decision trees, the agent just writes its own symbolic manual from watching. It removes the need for human-coded rule sets.
Which allows agents to get this complex domain-specific knowledge automatically.
And then use that structure to learn robustly and efficiently in domains that were just computationally intractable for pure exploration methods before. We're moving toward agents that don't just learn how to move, but learn why they should be moving in the first place.
This work has definitely provided a very clear, effective path forward. But before we finish, what's the immediate limitation here? What's the next big hurdle for researchers?
The framework achieved its really high accuracy because it was operating in environments that were, well, deterministic.
Meaning an action always leads to the same outcome.
Always. They were also fully observable and used simple integer-based states. That certainty in the environment is what allowed the induction module to produce a flawless symbolic rule.
A perfect symbolic manual only works if the world is perfect.
Precisely. If the environment were stochastic, if, say, an action had a 20% chance of failure, or if the world were only partially observable, the current induction module would likely fail. It couldn't produce a reliable, non-ambiguous rule.
And if that symbolic knowledge base becomes unreliable?
The intrinsic reward guidance fails, and in that worst-case scenario, the whole framework just collapses back down to being the original DRL algorithm, PPO, without any of its structural guidance.
So that raises a huge question for future work.
It does. Can the induction module be extended to recognize and infer probabilistic rules? Can it maintain that planning structure even when the world isn't perfectly certain? The future of truly robust AI planning really depends on conquering that uncertainty.